In the last section, we looked at comparing two means that were from independent groups. The data isn't always independent, though. So let's take a look at an example to motivate what we're talking about in this section. I want to get rich quick, and I think the best way for me to do that is to invent a fad diet and cash out quick before anybody realizes it doesn't really work. So let's invent Abel's statistically sound diet. We'll get marketing to work on that. Tighten it up just a little bit. But my trick here is going to be that it actually does work, and I'm going to show it with statistics. So let me gather some data. That's my plan. So I'm going to get some people, and I'm going to weigh them before they go on my diet. And I'm also going to weigh them after they're on my diet. So let's say I've got somebody that weighs 220 pounds. And after he goes through my diet, he weighs 210. And I've got somebody else that weighs 147. After she goes through my diet, she weighs 137. And I've got three more people. This person was at 334 and they went to 324. This person was at 185 and dropped to 174. And this person was at 286 and dropped to 276. Okay, so you can just take a look at these weights before and after, and just intuitively, don't overthink this. Just tell me if you think the diet works. And hopefully you'll look at that and say, it's not a huge loss, but it seems like it works. Matter of fact, it seems to work incredibly consistently. Like everybody loses 10 pounds. One person lost 11 pounds. But it's basically like, yeah, you'll lose 10 pounds on this diet. So that's great. It seems like it works. I would like to go ahead and prove that it works statistically speaking. So I would like to say that the average before is bigger and the average afterwards is smaller. So we'll call this mean 1 and this one mean 2. That's what I'd really like to show, is the before weights are bigger and the after weights are smaller. So let's go ahead and set up a hypothesis test and say, let's see, the opposite would be that mean 1's less than mean 2, and this one becomes the null. And this one becomes the alternative. The alternative basically says the diet works. So I'm really hoping I'll reject the null and support the alternative. So let's go ahead and get StatDisk fired up. There's StatDisk. I happen to have the numbers typed in already. And we want to go to, or we think we want to go to, hypothesis testing with means with two independent samples. So let's just use the method from last section. And we'll see why that's not actually the best choice. But let's go with it for the minute. So we're actually going to use data, and I'm hoping to show that the mean 1's greater than mean 2. I'll go with a 0.05 significance level, and then column 1 and column 2 contain my data. Keep in mind I'm hoping to reject the null and say the alternative is true, that this thing actually works. So we'll stay out of the pool, and we'll go into evaluate, and look at my p-value. It's like 42%. This is not an unusual sample. According to this analysis. And if you look at the confidence interval, it says, I don't even know if you lost weight or gained weight on this. It could be anywhere in this range. So both of them are saying there's no proof here that this thing really works. And I'm like, but it seems pretty clear that it does, like, again, very consistently. losing 10 pounds. So why did the test not detect that? Let's take a quick look at the graphical plot of these points. The before weights are the teal colored ones, and the after weights are the salmon colored ones. And the test that we just did said, hey, those two sets of data are pretty interspersed. And their averages are pretty close, and there's a lot of standard deviation. And it's like, there's just, those data sets don't seem that different. And what the test didn't know that we know is that these aren't some random blue dots and some random pink dots. This person is one person, and they went from, what was this? This is the 147 to 137. They went from there to there. And same thing, this is one person that went from there to there. These dots are actually matched up. They're not independent, right? This dot goes with that dot. And this dot goes with that dot. And once you look at that, you can see a pretty consistent difference. Without those little blue arrows I just drew, you're like, hey, I've got two data sets that are pretty darn close to each other. So the fact that these are not independent changes things for us. So let me go back. Let's get rid of this, because that really wasn't the right way to look at this thing. And let me create a third column here. And say, really, what we were all comparing in our brains, even if we didn't know it, is we were actually looking at the amount of weight lost, right? Because you looked at this first person and said, oh, they lost 10 pounds. And this person lost 10 pounds, and this person lost 10 pounds, and this person lost 11 pounds, and this person lost 10 pounds. And then we were looking at that and saying, again, you might not have realized you were thinking this in your head, but you were looking at that and saying, is the amount lost 0? Or is it greater than 0? And it's clearly greater than 0. It's right around 10, right? So I'm going to claim that when we have matched pairs, we're not really looking at two separate lists. We're really only looking at one list, the list of differences. That's what we care about with matched pairs. And the big question for us is going to be, did we make a difference? Is the difference 0? And it seems like the difference is not 0. It seems like it's around 10. So let me claim that this is really a 1 sample mean, not a 2 sample. And I'm going to claim that the mean, I was hoping that the mean was greater than 0. If you look at the book, they'll use a little sub d on there to remind you that we're talking about a list of differences, not one of the original measurements, not the before, not the after, but the differences. You can use that if you want to. I'm fine if you leave it off, as long as you understand that you're looking at this third list, this list of differences. And from there, we just need to do a regular 1 sample test. So let's set up the rest of the hypotheses. So the other claim would be that the mean, that the difference is less than or equal to 0. That becomes the null. That becomes the alternative. And I'm ready to run my test again. Actually, I need to put my new list in. So let me get back to stat disk. And actually right here, just in the third list, I'm just going to put in the differences list. 10, 10, 10, 11, 10. I'm not even going to use list 1 or list 2, so I'm going to look at list 3. So let's go to, we're in the wrong test now. Let's go to analysis, hypothesis testing. We want mean 1 sample. we want to say that our population mean is greater than the claimed mean of 0. All right. Remind yourself of the hypotheses here. The mean greater than 0 is what we're looking at. And let's see. We're actually, sorry, I should have clicked use data first. We're using data. So the population mean is greater than the claimed mean of 0. The column containing the sample data is column 3. And let's evaluate. Now look at that p-value, 0.00000. It's to 5 decimal places. It's 0. It's an incredibly unusual sample. If the mean's really 0, this sample's not going to happen. So now this time I'm going to reject the null. I'm going to say there is evidence that the mean difference is greater than 0. If you look at the confidence interval, it's saying, yeah, the difference is definitely greater than 0. It's right around 10, as a matter of fact. It's somewhere between 9.77 and 10.63. So that's really the only change that we have in this section, is we are going to consider not list 1 and list 2 as independent groups, but we are going to consider list 3, this list of differences, because these aren't independent groups. They are before and afters, and this list of differences is really what we're looking at here. So one little bit of good news. This was kind of an exploratory example. The good news here is we can make our calculations just a little bit simpler. Once we recognize that we have matched pairs, I'm not going to have to make this third list on my own. Turns out computers are really good at doing subtraction. And you figure the computer could probably do the 220 minus 210 on its own, and it's true. So go back to analysis, and let's look at hypothesis testing. So this is how you're actually going to do your homework tonight. You're not going to have to make that third list yourself. You're going to go to hypothesis testing. You are going to say, I recognize that I have matched pairs. So instead of picking 2 independent samples, you'll pick matched pairs. And you will pick the right alternative hypothesis. It's still that the mean difference was greater than 0, right? That we had a positive amount of weight lost. And now, again, we don't even need this third list anymore. I'm going to go and clear it out. Pretend that's not even there. You will need to put the original 2 lists into your sample editor here. But it just says, which 2 columns would you like to compare? I'd like to compare column 1 to column 2. And go ahead and punch evaluate. And, let's see, let's get me out of the way. So it does give you, it basically does what we just did on its own. So it creates that third list in its brain. It runs the p-value on that third list, says, yeah, the p-value is incredibly tiny. And it gives you the confidence interval in case you need that. And says, yeah, the average difference is actually, the average amount of weight lost is the difference we're looking at, is right around 10, right? It's 9.77 to 10.63. Exact same result as before. It just saves you that step of computing that third list on your own. Okay, so again, this was kind of the introductory example. In the next video, we'll take a look at a homework problem and do the full walkthrough.